Welcome to rfhammer.com. This video gives an overview of the microwave filter design and simulation software from rfhammer.com. You can download the software from rfhammer.com, save the exe and icon files to your PC. It may take a little while to open the first time you run it, but it should run on all standard Windows 10 machines. Right, the first window you see when you run the software is this one, where you can select between low pass, high pass, band pass and band stop filters. These are microwave distributed filters, and strictly speaking you only really get band pass and band stop, but you can use sections of the band pass as high pass and sections of the band stop as low pass. So these are the selections for low pass. We have two selections for high pass. These are the selections for band pass, and for band stop we have these two selections. Let's go to low pass. So here we can select redundant, synthesis, maximally flat and Chebyshev filters, generalized Chebyshev filters with one or three transmission zeros at infinity, and a low pass stepped impedance filter. Let's have a look at the redundant synthesis. So we can run this, and if you're familiar with rfhammer.com, you'll recognize this GUI. It's quite simple. We have four windows: the input window, the frequency plot window, the circuit diagram window, and the component value window. So the circuit diagram, you have a slider which you can slide the circuit around to see the complete circuit, especially for higher orders. Similarly with the component values, another slider which you can then move that around to see all the values. For the component values, for example for Z1, we can go to the circuit diagram and we see Z1, L1. So this is the first first shunt open circuit stub. So it has an impedance of 180.9 and an electrical length of 45 degrees at FC, where FC is 4 gigahertz. Right, so for the input we can input all the filter design parameters, and we can run that. In this case we have a response of a maximally flat filter, so we can select between amplitude, phase and group delay. Over here we're displaying the amplitude S21 and S11. Right, let's select Chebyshev. We can run that. So we can select between maximally flat and Chebyshev. We have a Chebyshev now. The filter order is 5. I think we can go up to 11. We can run. Okay, there we see a 11th order redundant synthesis filter. We have the impedance, filter impedance. We have the attenuation factor of the transmission lines. We have the ripple, that's only for Chebyshev, which we can vary. And for Chebyshev only we can vary the cutoff frequency between 3 dB and equi-ripple. The plot has a system impedance of 50. You can vary the start and stop frequencies of your frequency plot. In this case it is 1 gigahertz and then stop at 11 gigahertz. The number of frequencies you can increase to get a smoother plot or to increase the accuracy of your marker. And then the marker we can move around. We can make that at 4 gigahertz, and the marker would go to 4 gigahertz. Okay, the attenuation factor we can also vary. For example, now in this case we can see the loss of the filter. If we want a lossless filter, we can make that 0 and run that, and we get the ideal filter. But 3.5 is perhaps a realistic value. Right, let's go back to 5, order of 5. We can run that. Right, so we see we can select between cutoff of 3 dB and equi-ripple for Chebyshev. In this case we can see we have a 3 dB cutoff of 4 gigahertz. We can change that to equi-ripple, and we can see now that 4.1 dB ripple, this is the ripple we have, and so here's the ripple, and we can see the cutoff frequency at 4 gigahertz is the equi-ripple cutoff frequency. Okay, the filter impedance and the system impedance. If you want to design a 75 ohm filter, we can make that 75 and run that. And we see the response is not as we expect, but that's because we are measuring it in a system impedance of 50 ohms. In other words, your network analyzer is 50 ohms. So let's measure it with a 75 ohm network analyzer, and we get back to the expected response. But obviously your component values have now changed. Right, so that was the redundant synthesis. Okay, for the generalized Chebyshev, let's have a look at one transmission 0, so we can run that. Right, so we can select the attenuation. This is the stop band attenuation, so we can see here it's set to 60 dB. We can change that to 40, and then this goes to 40 dB. We can select between 20 and 26 dB, so the return loss at the moment it is set at 20. Let's put that back to 60. Okay, this is all very similar as explained, but we see now that in this case we have a series short circuit stub, which is not really realizable in microstrip, strip line, or suspended strip line etched circuits. It's difficult to realize. So this gives us the option that we can select on transmission line to replace the series short circuit stub, which then makes it more compatible to etched circuits. So we can run that with the transmission line, and we see that the stop band rejection has degraded. That's because we are using a approximation with the transmission line. But if we go to the 3 transmission zeros, and we can select transmission line, we run that, we can see the transmission line, the rejection, stop band rejection with the transmission line is not looking too bad, and we can improve it further by increasing your impedance of the transmission line. Right, so that's improved the stop band rejection. Okay, let's go to stepped impedance. We can run that. Right, so we once again can select between maximally flat Chebyshev and Bessel. Let's select Chebyshev. Okay, so there we have a response of a 5th order. We can make that a 6th order if we wanted to. Okay, so we also see that we have an option to select between your first element being a low impedance, Z0 low first, or your first element being a high impedance, Z0 high first. Okay, so we can select that. So we see we get most probably a bit better rejection in the stop band with a Z0 low first, a low impedance element first. But we notice that, let's put this into the cutoff frequency, 4 gigahertz. Okay, so we notice the cutoff frequency is not correct. This is due to the approximations we're using. But you can, let's put this back to 5, for example. And we can then play around with the cutoff frequency, and we can adjust it, and we can see we can adjust it until we get the desired cutoff frequency, and we can then use those component values. Right, let's go to high pass. So in high pass we have the options of generalized Chebyshev, one of 3 transmission zeros. Let's have a look at one transmission zero. Okay, so there we have the response. Once again, we can play around with the attenuation and the return loss. And we see in this case we have a series open circuit stub, which once again is not suitable for etched circuits. But here we have the option, we can select a coupled line instead of the series stub. Okay, let's make that 40 for example. Okay, we notice that your pass band here is increased, which is nice. So you can also play around with the attenuation to maximize your high pass pass band. Okay, so now we can select coupled, and we see that the return loss has degraded, but it's still not too bad. And we now have a coupled line in place of in place of the open circuit stub, which is nice for etched circuits. So you can also vary the impedance of the even mode coupled line, ZOE, and you can then see this to see if it improves the reflection coefficient or the return loss. Right, that was high pass. Let's go to band pass. So band pass, we can have a non-redundant synthesis for maximally flat and Chebyshev coupled line filters, shunt short circuit stubs with transmission lines, shunt open circuit stubs with transmission lines, and then a capacitively coupled filter with shunt short circuit stubs. Let's go to the non-redundant synthesis. So what do we mean by non-redundant synthesis? Well, it means that the filter order will be equal to the number of elements, the number of components you have in your filter, which is very nice because it makes it very compact. If you have a non-redundant, then you get many more elements than the filter order. Okay, so once again, we can select maximally flat Chebyshev. Is the maximally flat Chebyshev, we can run that. But once again, we see here there is a series open circuit stub. If we go to 9th order, you can see there's two. At the moment, we only have the 5th and 9th order, but in 9th order, we have then two series open circuit stubs. And we can now once again replace those with a coupled line. So let's just go back to a 5th order so we can see what's going on more easily. Okay, so we can now select a coupled line, and then it will replace the series stub with a coupled line. And the reflection coefficient, the return loss, is not looking too bad. Right, so we also have the attenuation factors for the transmission lines and the coupled lines, which we can input. We have upper and lower cutoff frequency, and this is basically more for a wideband type filter. Now, using the coupled line, so we insert a unit element, but we still end up with a non-redundant synthesis, so we still only have 5 elements for 5th order, so it's still redundant in that sense, but a maximally flat doesn't lend itself to this approach, so at the moment only the Chebyshev selection is implemented using the coupled line. Yeah, and as I say, we can go to the 9th order, and we can then also look at the response with a coupled line. If the return loss is not looking too good, you can perhaps play around a bit with a ripple to see if that improves it. Right, so as I said, this is a wideband filter, so if you make the filter too narrow, then the value of your coupled line and the value of your open circuit stubs will increase, and it might make it then difficult to manufacture. But let's just then change this to 10 and to 6 as more narrow bands. So the filter can still be synthesized, but you can see in this case the coupled line impedance has increased, and the series stub as well. So it must probably not be really practical to make this filter. Right, okay, the coupled line filter is well known. So it's coupled lines. You'll have one more coupled line than the order view filter. Here we have a fifth order, and we have 6 coupled lines. We can then select between Chebyshev and maximally flat. We have the attenuation factors for the coupled lines. The rest is the same. We can make the attenuation factors for the coupled line 0, and then we should get a lossless filter. So let's have a look at that. Sorry, I changed the ripple. Okay, so we make that 0. So your attenuation factors are now 0. Let's run that. So we get the ideal filter. And we can have a look at the group delay. Okay, there we see the group delay. But I think 3 and 1 are realistic values for coupled line. Okay, so there we have the coupled line filter. Okay. Band pass with shunt short circuit stubs. So here we have a filter with short circuit stubs, shunt short circuit stubs, separated by transmission lines. We can have, once again, maximally flat and Chebyshev. All the rest is more or less the same. Once again, this is more a band pass type, a wide band pass filter, but you can reduce the bandwidth. You just have to see then if these element values will still become realizable. So what should we make that? 10 and 6. So it's going to be a bit more narrow band. Okay, so you can see the element values have decreased. So the more narrower the bandwidth, the lower these element component values are going to be. And you'll have to see if they can still be made in the form of an etched circuit. Okay, but it would be nice then to replace the short circuit stubs with open circuit stubs, and that's what the next filter does. So let's have a look at that. Can run this. Okay, so now we have shunt open circuit stubs, parallel open circuit stubs, which is very nice, much easier to make in etched circuits. But there is a trade-off that around DC you get a pass band, so you must just be aware of that. Let's make this a low frequency. Yeah, and then you can see around DC then also have a spurious pass band. So just remember that. That's the trade-off for using these open circuit stubs. Right, yeah, and you can select between maximally flat as well. Right, okay, the last bandpass filter is the capacitively coupled. Let's run that. So this is more or less, I suppose, a ceramic type filter, which is very popular these days, especially at the lower frequencies, where you have series lumped element capacitors and parallel short circuit stubs. So in this case, the design does not have all these stubs the same impedance value. The stubs have different impedance values, which helps a bit with the response. So that's the 6th order, the 7th order. Okay, so there we have the response. You can play around a bit with the ripple. It's not exact in terms of your return loss, but it's a very popular filter which is used these days. Okay, let's then proceed to band stop. So in this case we have a non-redundant synthesis with maximally flat and Chebyshev, and then we have the redundant synthesis. Let's have a look at the non-redundant synthesis. Okay, once again we can select between Chebyshev and maximally flat. Chebyshev case is the 5th order, and once again, as expected, for non-redundant synthesis of a 5th order we have 5 elements. So it's easy to realize the values are fairly close to 50 ohms, and when you have five elements, so it's very nice and compact and small. And I think in this case, not sure, might be 11. Okay, so we can have orders from 3 to 11, odd orders 3 to 11. Okay, so this will be 11th order. There we have the 11th order. Okay, let's go back to 5, because what we can also do is we can compare this now to a redundant synthesis. So with a redundant synthesis, obviously we are expecting more elements here now, because it's redundant. Okay, so let's then go to redundant synthesis and run that. And this is really nice now because we can have simultaneous windows and we can compare responses to see how they compare. Okay, let's just make all the inputs the same. Okay, so this must be Chebyshev. For Chebyshev, we have equiripple because the non-redundant is equiripple. What else is there? Okay, the cutoff frequencies are 12. Upper is 12 and the lower is 4. Just check here. We have a plot starting at 1. Let's run that. Oops. Okay, let's check what's going on here. We've made a mistake here with inputting the data. So let's change that. That should be 4. Right. Okay, so let's just check Chebyshev. This all looks the same. Okay, so it looks the same. Let's have a look at the frequency response of the two cases. So on the left we have redundant, on the right we have the non-redundant. Okay, so there we can see the two responses. Okay, so there they are compared. Let's have a look at the circuit diagrams, and as expected, over here we have 9 elements, okay, and for the non-redundant we have 5. Okay, so we can then see the responses in those two cases. But we can also then, for example, look at the redundant has 9, so let's have equivalent number of elements for the two cases. And so we have the same number of elements in each case, 1, 9, and 9, but we can see now that your cutoff is, let's just move this, cutoff is quite a bit steeper in the case of the non-redundant case for the same number of elements. Okay, so I think we've covered everything. So thank you for watching this video. I hope it was informative, and remember to visit rfhammer.com. There's quite a lot of other software, design and simulation software available at rfhammer.com. Thank you.